Welcome back to Finite Element Methods. We've been talking about the Stokes problem for the past one or two lectures. So before we get into the meat of what we want to talk about, let's just review pretty quickly what the Stokes problem looks like and how to get the weak formulation for that. We touched on that briefly before, but let's do a couple of calculations. So the Stokes problem is we're looking for a velocity and a pressure that satisfy this equation when I'm given some forcing function f. This is what is called the divergence-free condition, and this is what we call the no-slip boundary condition. So the first thing we want to do when we meet this Stokes problem is to rewrite it in the weak formulation, because that's the formulation that makes sense for us for developing finite element methods. So what we're going to do is multiply by a test function and integrate by parts. So the test function that I want to use is one that is from this space. This is the space. This is essentially the same space of solutions that I'm going to expect or the same space that I'm going to expect my solution to be from. A Hilbert space, H1 a Sobolev space of order 1. With zero boundary conditions for each one of the components of the test function v. So that's the type of function we're going to multiply this equation by, and then we're going to integrate. So there we go. And the first thing we want to do is recognize what is this Laplacian u. Well, it simply means the Laplacian applied to each one of the components of u. And how many components of u are there? There are d components. So this really represents a dot product between two vectors. And so that's why I have this sum here. That's the sum for the dot product. It was inside this integral, and I'm going to remove it to the outside by the linearity of the integral. And so now we have the sum of the Laplacian of ui times vi. So the dot product goes away because well, it doesn't really go away. It transforms with this summation, and we have this to contend with. Now, the reason why I wrote it that way is because now we can apply our integration by parts formulas as before, applying it to ui and vi. So we're going to remove a derivative from the ui and place it on the vi. When we do that, we're going to change the sign. The sign goes from plus or minus to plus. And so we have this integral plus a boundary integral, or minus a boundary integral, technically. The boundary integral vanishes identically because the functions from our test space, v, have the property that each one of their components is 0 on the boundary. So that for each I, this guy is equal to 0. So that's why that goes away. And then all we're left with is this term. That term is precisely what we're going to define as A, U, and V. And A, U, and V is precisely the term I just wrote. But we have now a dot product here. Why do we get a dot product? Well, when we remove this derivative from this derivative operator, it's really the divergence of a gradient. And so when I throw it over to the other function, it becomes a gradient, and I have gradient dot gradient. That's exactly what I have here. Now, what is a gradient operator? It's really just, well, it's easiest to think about it like this. It's, of course, a vector. So we're dotting two vectors. And so I'm going to bring out another summation associated to that dot product. That's going to be, or have the index j. And so that's du di dxj, dv di dxj. And so that's what this term becomes. Again, I had a summation that was inside and I brought it out to the outside using the linearity of the integral. Okay, so this is exactly how we defined this bilinear form previously. Another way of writing it is using what's called the matrix inner product notation, this double dot notation. So what I can think of is, or how I can think of this operator on this vector is as follows. This is like the Jacobian of u, okay? Or I can think about it like this. This is the gradient of a vector function u. How could I define that? So it's really a matrix, okay? The gradient of a vector function u is really a matrix of the following form, dui dx j for j and I between 1 and d. So it's a d by d matrix. Okay, if I have two d by d matrices, then I can take their matrix inner products with each other, and that's precisely what that symbol represents here. Okay, this is also a d by d matrix, also a d by d matrix, and so we're just using that matrix inner product notation. So the weak form of the Stokes problem, we're almost there because we've only taken care of one term, but it's the harder of all the terms. Multiplying this by the test function and integrating by parts. We're going to do the same with this gradient pressure term, and all we're going to do is throw the gradient that was on the pressure over to the test function. That picks up a minus sign. It doesn't involve a boundary term, and the reason is because of the test functions that we're using. So what we can say then is we can characterize the weak formulation of the Stokes problem in the following way. We're looking to find a u in this space. The nice thing about the weak formulation is we don't require u to be all that smooth. So if you look back at the classical definition of a solution to the Stokes problem, we're asking for a C2 function. Here, we're only asking for a function which is weakly differentiable and only up to first order. Okay, so we're eliminating a lot of unnecessary stuff. So there's a missing arrow over that. We're looking for u in this space that satisfies this problem. Okay, so as I said, this is the term that we just derived, the bilinear form A. The bilinear form B, where does that come from? This guy is precisely equal to BV P is going to be P divergence of V. P divergence of V in the L2 inner product. That just comes because we take the gradient that was on P and we throw it onto the test function. We pick up a minus sign when we do that, and we don't have any boundary term associated to doing this because of where the test functions are coming from. Boundary term goes away. So you can check that out. So clearly this is the first equation in our weak form. What about the second equation? So the second equation, all we're going to do is multiply by a test function q and integrate. We don't need to do any integration by parts. Because of the way this is defined, this BUQ, that means the L2 inner product of Q against the divergence of U. Divergence of U in the strong form was assumed to be 0, so in the weak form, we're just going to take this bilinear form to be equal to 0. Now, the plus or minus sign out front doesn't matter because on the right-hand side, I have 0. So I could multiply this by another minus, and it's not going to change to 0. So this is our weak formulation of the Stokes problem. We mentioned this last time, but that was just a little bit a more in-depth derivation. This bilinear form A that we introduced above and this bilinear form B here that we've just defined are very important for analyzing the Stokes problem. Their structure is it's important to understand. Let's go on to another space that we defined last time in equation 22.3. This space we call V. Oh, and by the way, I want to go back up here just a little ways, something that I highlighted in red. From basically some point on, I'm going to stop referring to this space should be H01D. That just means all D components of the vector are H01 functions. Okay, so we're going to introduce this notation X to represent this space here. Okay, so that's the space of the test functions for V and also the solution U. Okay, that's also X. And what about our pressure functions? Our pressure functions are going to come from this space, Q, which is by definition L02. So these are mean zero L2 functions. Let me just remind you. L02, that was defined as space of all functions that are in L2, but also have mean zero. So if I integrate against 1, I get 0. So why am I calling this the mean, mean 0? Well, it's equivalent to the mean. The mean would be when I divide by the size of the domain. But of course, that doesn't matter when I'm using 0 as, or expecting 0 as the mean. This is a linear space. In fact, it's a Hilbert space because it's a closed subspace of a proper closed subspace of L2. So it turns out that it's also a Hilbert space, right? So that's where we're going to ask our pressure to come from. The reason why we're going to ask pressure to come from that space, actually, I should have said here, find U in this space, and I forgot to say something about pressure. But the pressure we're going to ask to come from this space. The reason why we're asking pressure to come from this mean zero space is this is going to allow us, this restriction right here is going to allow us to guarantee that pressure from this space is unique. If we'd only asked for pressure to come from L2, then it wouldn't be unique. The reason why is because if P was a solution to the Stokes problem, then we could add any constant. Okay, so we could say, well, then P plus alpha, where alpha is a spatial constant, will also be a solution. So, and that can be seen from right here. Whenever we initially define this, that's because the gradient of any constant function is just going to be 0. So constant functions don't enter into this problem at all. Sometimes we say this or express this as follows. The pressure can be redefined up to a constant or is unique up to a constant. So that's the reason why we're asking pressure to come from this space. That eliminates the possibility that a constant could be added to the pressure. The only constant from this space, constant function, is the constant function 0. So that means we're going to be able to expect pressure to be unique. And we'll show this when we prove that the existence and uniqueness of solutions to this later on. All right, so now we want to move on to this definition, this space V. So V is a subspace of H01D such that when so it doesn't hold for all. So this is a characterization of a special place in this set. It's the set of all V such that when I integrate against Q, or not integrate against Q, but when I look at this bilinear form, this is just an L2 inner product. So in other words, when I take Q against the divergence of V in the L2 inner product, I get 0. Right? So we're looking for all V such that this happens for all Q in L02. So this is a special subspace. We characterized this last time. We said that V is a closed proper subspace of V, and therefore V is a closed proper subspace of H01, and therefore it's a Hilbert space in its own right. And this allows us, as we explained last time, I'm not going to go into all the details of this again. This allows us to characterize a related problem to our Stokes problem. If UP is a weak solution to the Stokes problem, this implies that U is a solution to this problem, a lot simpler. In this case, V or U, the solution comes from the space V, and the test functions can be taken from V as well. So I'm not going to prove this again. We argued for why this is the case last time. But why is this nice? The reason why this is nice is we can use Lax-Milgram, or even easier, we can just use Riesz representation to show that we have a unique solution to this problem, right? So the solution comes from V, the test functions are from V. So this is a nice symmetric problem, and we can apply Riesz representation or Lax-Milgram theorem to get or guarantee that we have a unique solution for this problem. Well, this says if U is a weak solution to the Stokes problem, then it must also solve this problem, but we know that this problem has a unique solution, okay, at least for U. Well, this is going to tell us how to transform the problem in order to find P, which is what we're going to do next. But we're going to get onto that momentarily. Oh, just a pictorial representation of what I said earlier. V is a closed proper subspace of H01, H01D in particular, and therefore this is a Hilbert space by itself. And so why can we transform the Stokes problem that we showed above, or the weak formulation of the Stokes problem, into this simple problem? Well, that's going to be that we explained last time, but also maybe make that a simple little homework exercise so you can think about that a little bit more. All right, let's move on, because now, well, we know that essentially that we can always expect to find a solution U to this problem, and therefore we can also argue that that is going to be our solution to the Stokes problem that we're seeking. But it doesn't tell us anything about the pressure. In order to get a solution for the pressure problem, we're going to need some more machinery. And the machinery that we need comes in the form of something which is rather well known, and it's called the Inf-Sup condition. So we're going to review a couple of facts that we mentioned last time, but will be nice to have before us as we go on here in class 23. The first one is a definition of this V perp. So suppose that V is as defined above in 22.3. So that's that. So V perp is going to be defined as the orthogonal complement of V with respect to some bilinear form or inner product. And specifically, we're going to use the A bilinear form. So here's how we define this. We're looking for the set of all V in H01D such that V is orthogonal to U in this bilinear form A for all U in V. So basically, we're looking for a space. Kind of the best way to think about it is, let's just think about the space in R2. So if we look at this and identify this subspace of R2 as V, then what is V perp going to look like? Well, it's also going to be a subspace. And so it's basically going to look like this if we're using the standard L2 norm as our metric, okay, as our way of measuring angles. Then anything we take from this space, okay, is going to be perpendicular to anything else that we take from that space, okay? You can look at it like this. A vector in this space V perp and a vector in this space V are going to be at right angles to each other. So I can't draw the same sort of thing here in this space, um, it's too complicated looking, too blobby, but it's easy to see here in R2. So we're looking for a set of all vectors V in the larger space such that they are all orthogonal to everything in V. Okay, so the structure of this is quite complicated, especially in this infinite dimensional setting. We can't picture it. The drawing above is kind of the best picture for this space. But this space is going to be useful and special for us in our analysis. VPerp. It's the orthogonal complement, as I said, of V with respect to this bilinear form. And both of these spaces are inside of this big parent space H01D. So V and VPerp are so when I think about finite dimensional things, we can decompose the space as a direct sum of V and VPerp. In infinite dimensional space, it's not so easy to make claims like that. You have to do a little bit more work to prove such a thing. But that's kind of how you can think about this space. We can think about this space as being decomposed as V and VPerp, but not exactly. Okay. So that's fine if you're in finite dimensions, but because we're in infinite dimensions, we can't exactly think about it like that necessarily. You need a little bit more machinery to understand that decomposition. But in any case, here's a theorem that one can prove and will be quite useful for us when we try to establish this thing called the Inf-Sup condition. Given any q in L02, so this is the L2 space of mean zero functions, or the L2 subspace of mean zero functions, there exists a unique V. Where is that V coming from? It's coming from VPerp, such that the um, the divergence of V is exactly equal to Q. So this says, in other words, that the divergence operator is an isomorphism from this space, that's the domain, into this space, the range. An isomorphism, a one-to-one onto mapping. Moreover, there exists a constant such that um, and this is going to be independent of V and Q, such that V's H1 seminorm is less than C times the L2 norm of Q. Okay, and again, this constant will be entirely independent of V and Q. So we don't have the required machinery with us here to prove this, so we're just going to punt and refer to this reference, Giralt and Ravière from 1986, famous result or famous book on finite element methods for the Navier-Stokes equation. All right, now we're in a position to prove this famous Inf-Sup condition, even though it doesn't look like an Inf-Sup condition that maybe some of you have seen yet. We'll get to that modified form, which will be that famous Inf-Sup condition momentarily. So we're going to prove this precursor. There exists a constant beta greater than zero such that the sup taken over all V in H01D, as long as V is not equal to zero, of this quotient is greater than B times the L2 norm of Q. Okay. And this holds for all Q in that space of the L2 subspace of mean zero functions. Now the quotient that we're looking at here is quite important. So we should decompose it. So what's on the top? What is on the top is essentially the B bilinear form. So this on top is nothing other than B V Q. Okay, so that's what's on top. We could replace it with that. And what's on the bottom? The thing on the bottom is just going to be A, V, V, square root. So that's maybe that's an easier way to memorize what's happening here in this Inf-Sup condition. Okay, so you've got B on the top and square root of A on the bottom. If I take the supremum of all the quotients that I can form this type, as long as V is not equal to 0, then this is always going to be greater than some constant, which is independent of Q, times the L2 norm of Q. So this is what we want to prove, this very strange, very weird thing, which is going to prove to be useful for us in the analysis that we do below. All right, so don't worry so much about what this means. We're going to see how it's useful, and the utility of this object is going to give meaning to it. All right, so let's start off by letting Q be an arbitrary function from this mean zero set of functions, but we don't want it to be trivial, so we don't want it to be equal to 0. Otherwise, let it be arbitrary. Then that theorem above tells us that given any Q, we can find a V from V perp. We're going to give that a special name. We can find this V in V perp such that it satisfies this equation. We're going to give it a subscript Q, and that will tie it to Q. Okay, that will tie it to Q. But what does this imply? This implies if we simply multiply by Q and integrate, then this is saying this object here is equal to this object here. We're just going to multiply by Q and integrate over the domain. Of course, this is nothing more than BVQ Q. Okay, that's that object, but we'll come back to that momentarily. We've just shown that we can always find a VQ from this space, VPerp, such that it's exactly equal to the L2 norm of Q. So we start out with Q and we manufacture this guy, and it has this property. What else do we know? Well, from that last theorem, the theorem that we couldn't prove from Giralt and Raviere, we know that the H1 seminorm of VQ is less than that constant times the L2 norm of Q. And this constant is completely independent of Q. All right, so now let's write this guy on the top and this guy on the bottom. So we'll make the quotient involving this Q is arbitrary, and this VQ is the thing that we chose to satisfy this equation. Okay, so we can always find such a V to satisfy this. We showed that that is equal to the L2 norm of Q squared. On the bottom, we still have the H1 seminorm of VQ. We know that this inequality holds, so let's write this in a reciprocal form. So if this inequality holds, then what is the reciprocal of this? It's going to say that 1 over, we just need a seminorm here, VQ H1 seminorm is greater than the reciprocal of what we have there. Okay. As long as neither of those two objects are equal to 0. And the only way they're going to be equal to 0 is if Q is equal to 0, because we have this isomorphism. But Q is not equal to 0 by assumption. All right, so we have this inequality, so we're going to replace this guy, 1 over that, with this smaller thing. When we do that, we get to cancel this square and this L2 norm of Q, and we just obtain that the L2 norm of Q over C is less than or equal to this object. Now, all we have to do to get the object that we want is to observe that this is a very special V. it's that one that's related to Q through the solution to this equation. If we were to take the supremum of all objects which look like that and replace V by something arbitrary in H01D, as long as V is not equal to 0, then this has to be, this object here has to be less than the sup. Why? Well, the supremum, it's easy to understand why that's true if we reinterpret the supremum using its English name, which is the least upper bound. So this is an upper bound for things which look like this. That's kind of obvious because this is a particular element from this set. In fact, this element comes from vperp, but vperp is a subset of that set. So clearly the upper bound for all things of this type is going to be bigger than this object here. And that's exactly what we have. Okay, the great or the least upper bound in other words. All right, now just make the connection of the inequalities. So this object is greater or equal to this object, which is greater than or equal to this object. And now we have it because what we wanted was something with the norm of Q over here times a constant. Do we have that? Yes, we have this constant here, which is 1 over C. So if we just take beta to be equal to 1 over C, we get the result that we were looking for. So that is this precursor for the Inf-Sup condition. The actual condition is called Inf-Sup because we take an infimum over Q, and this is incorrect here. There we go. That Q is not a vector. Okay, so what we're going to do is we're going to start with this object here. Okay. Notice that this object works for all Q. Okay, so we're going to assume we're going to assume that Q is not equal to 0, and we're going to divide both sides by the norm of Q. As long as Q is not equal to 0, we can divide both sides by that. And then we get a bunch of objects, okay, a bunch of this supremum with this object, which is greater than beta. So that, what is that saying? That's saying that, let me write that intermediate form. Okay, so if I have that, okay, this object, we're going to put, and we know that this is going to be greater than or equal to, for all Q, not equal to 0. Of course, Q is in this space L2, 0. So what do we know about this? Well, for all quotients like this, well, actually all numbers like this, we have a lower bound, a beta. Anytime you put in this Q, so this guy over here only depends on Q. We can kind of think of it as like a function. Function of Q, as long as Q is not equal to 0, is always bigger than beta. Well, what do we know about that object? Well, this is a lower bound for this objects of this type for any Q. That means we can take the infimum over all Q of this type of this object and still get that bigger than beta. Why? Well, because this is a lower bound for objects of this type. This is a lower bound of objects of this type. And now what is the infimum? The infimum is the greatest lower bound. Well, an object which is the greatest lower bound is certainly going to be equal to an arbitrary or some run-of-the-mill lower bound. So the greatest lower bound is bigger than any other lower bounds. That's why we can take the infimum and know, because what is infimum? Infimum is the greatest lower bound. That must be bigger than this lower bound beta. And so this is what we call the Inf-Sup condition. And it's called Inf-Sup condition because it has inf and sup. Okay, again, this is going to be our B bilinear form. Now we're going to have two objects in the denominator. We have the L2 norm of Q and the H1 semi-norm of V, both in the denominator. We're going to take the supremum first on the inside over all vectors V and H01D, as long as V is not equal to 0. That gives us a function of Q. And from the last result, we showed that that function of Q for every Q is bigger than beta as long as Q is not equal to 0. So that means now we can take the infimum over all such possible values. And the infimum means the greatest lower bound, and this is a lower bound, so the greatest lower bound beats any other lower bound. Okay, so this is what we call the Inf-Sup condition. It certainly follows from the previous condition. You can also show that if I know this, then I can prove something like this is true. Okay, so you can go from one to the other, doesn't matter. Let's eliminate that because we don't need that now. So Inf-Sup condition. So what we say is that X and Q satisfy the Inf-Sup condition relative to this inner product B. So that we say the pair X, which is H01D, and Q, which is L20, satisfy the Inf-Sup condition relative to this bilinear form B. Okay, this is our Inf-Sup condition, and this is our Inf-Sup pair. And later on, we're going to try to prove Inf-Sup conditions for other pairs. Okay, now notice that this condition has nothing to do with Stokes problem. It only has to do with the structure of our B bilinear form. It kind of has to do with the structure of the A bilinear form too, if you think about A being there. But in any case, it only specifically deals with the B bilinear form and these two spaces, and that's it. Okay, so from above and last time we showed that if we had a solution to the Stokes problem, then it was the unique solution to this problem where the test functions are from the same space as the solution, this space we called V. Okay, and there's V once again. Now, what this means is that once we have U, a unique solution for U, we can show that, we can argue that, well, now that we have U, we can get P from going back to the original Stokes problem. So if I remember the original Stokes problem in the weak form looked like this. Okay. But now suppose that we know that U exists and we want to figure out, well, does P exist? So now we're going to throw this guy over to the other side. And we're going to treat that as what we call data for the problem. Just like we call F data, now U is going to be treated as data for the problem. And we're going to look for P, which solves a certain problem. Okay, throw this to the other side. This we're going to ignore. We don't need this now. We're only looking for P now. And we're going to treat U as known, throwing it to the other side. So that's precisely what we're doing here. We know that U exists, and now we want to figure out, does P exist for the original Stokes problem? Knowing that U exists. U has to live in this space. That's already known from the beginning. Or not, at least, if not from the beginning, very early on in the game. Okay, so this looks like a standard problem that we've looked at before, except it's a little bit funny. We're looking for P such that it solves this problem for all test functions V from this test function space. Now we need to take V not being from this little v is not coming from that capital space V, but it has to come from this space H01D. Okay, so once U is determined, we're going to find P that satisfies this problem. And we're going to treat all of this as known information. Okay, basically we're treating F and U as known information, and this gives us a known problem to solve. Now, to solve this problem 23.3, we need an abstract version of the Lax-Milgram lemma. So that's what we're going to prove next. Or at least not prove it, but state it. Now, normally when this generalized Lax-Milgram is stated, it's stated with an A, but I've designated A to mean something else, and so we're going to call it a twiddle. So let U and V be real Hilbert spaces, and suppose that A U cross V to R is a continuous bilinear form. Let L be a bounded linear functional on V. Okay, so the second space. We're going to assume further that this A tilde satisfies something that looks like the Inf-Sup condition. In fact, it is precisely an Inf-Sup condition for A tilde. Okay? So assume that A tilde satisfies this Inf-Sup condition. Now look at the placement. A is on A twiddle, or A tilde is on top. So that's going to take the role or play the same role as B plays in our current problem. The last thing we have to assume is that the supremum taken over U in this big space U. I don't want to write it like that because then I get there. This is my space. There's my object. We're taking the supremum over all U in capital U of A tilde UV. And we need to assume that that's greater than 0 for all V in V, as long as V is not equal to 0. We'll come back to this one momentarily, but this one, if we interpret things right, this is already something that we proved for our Stokes problem. Okay, as long as we think to ourselves that A tilde is going to take the role of B, or B takes the role of A tilde. If all of these assumptions are true, that this is a continuous bilinear form, satisfies the Inf-Sup condition, and satisfies this special condition, then there's a unique solution U in, I want to change that, capital U in capital U, that satisfies this equation. And this looks like a normal, ordinary run-of-the-mill equation. In fact, it's precisely the equation that we have going on here. Okay, precisely that of the equation we have here. What's to notice about this equation is that the test function space and the solution space are not the same. Test function space and the solution space are not the same. So this is a special type of what's called an asymmetric problem. The test function space and the solution space, test function space and solution space are not the same. But you can still, under certain circumstances, show that a problem of this type has a solution. In fact, we can use this generalized Lax-Milgram lemma to prove exactly that. Moreover, once we have a solution guaranteed, we can show that the U norm of U is less than or equal to the operator norm of that bounded linear functional L divided by the alpha that comes from the Inf-Sup condition here. Okay. The proof of this is beyond the scope of what we want to talk about here today. And we didn't prove the Lax-Milgram lemma or the Rees representation theorems either. These are theorems from functional analysis that are quite important and useful to what we want to do. So we're going to rely on our reference for that, and we're just going to use this to prove that the solution to our pressure problem exists and is unique as well. Okay, so this is our pressure problem, the so-called pressure problem. Let's see, gone a little long. Okay, here we are. Okay, so we're going to take that from Atkinson and Hahn, and now we're going to try to reinterpret the pressure problem from above in the language or the context of the last result. So this B function is going to play the role of the A tilde function. Now we can interchange the orders of these two. Well, not here, but um, how do I want to put it? I guess we're interpreting this BVQ as being A tilde QV. And the fact that I've reordered Q and V in those respective positions doesn't matter. Okay. All that matters is it has to be a bilinear form, has to satisfy the Inf-Sup condition, and we will show that it does. Okay, so A tilde QV, that's going to be our B bilinear form, which is defined like that. Remember, that's the thing that has to appear on in the numerator for that Inf-Sup condition, in the quotient that appears in the Inf-Sup condition. Has to appear in the numerator. U we're going to take as that space of L2 mean zero functions. V we take as the space. Again, this is not the same V as we had above, so maybe I should give this a tilde, but I hope that you understand. This is not the same V that we mentioned above. This is a different V. This is the V coming from the assumptions of this problem. So it's generic. So V should be taken as H01D. And what about that bilinear, not bilinear form, but the bounded linear functional L in the solution here, uh, in the solution of this problem? Well, we need to take that as AUV minus FV. And the difference in the sign that you'll see from that problem that I wrote above is that I'm going to absorb the minus sign. Okay. So multiply both sides by minus, and so this means that this should be AUV minus FV. AUV minus FV. So now we've identified everything. Now, except for, uh, well, let's go back and check. Do we have the Inf-Sup condition? Yes. So that 23.4 condition that we need to check. Well, now that we've identified this as B, this is going to be B VQ on the top, and everything is going to work out perfectly then thereafter, because we can identify that as being exactly the Inf-Sup condition that we had previously, which was 23.2. So the only condition left to check is one that I'm going to let you guys check as an exercise. That's 23.5, namely that this is positive for every v and v. So this can be thought of as a function. Now, once I take the supremum, that takes away the dependence on u, and so this is just a function of v. Okay, so this function of v has to be positive for every v. Well, we can, if you look at it in the language of the Stokes problem, what we have to show is that the supremum of every q and L02 of this object has to be positive. That's the B bilinear form, which plays the role of A tilde that we had above. Well, we can almost get there really quickly, but we don't quite get all the way. So if we fix V in H01D, then we could take Q to be equal to the divergence of that V. Do we know that the divergence of V exists? Yes, it's going to be of an L2 function, because if we take it from this space, if we take V from that space, we can clearly take first order derivatives, we can add them together, and that gives us a function that's back in L2. How do we know that Q is going to be in L02? We'll just integrate this object. Okay, if I integrate that object, then so if I integrate the divergence of V over the set omega, then using the divergence theorem, this is going to be V dot n ds But V comes from the space H01. Each of its components is equal to 0 on the boundary, so this integral is just 0. So this is a mean zero function. Therefore, this is a mean zero function, if we define it that way. So the only missing piece then is we can go ahead for every V, we can sub in for that Q divergence of V, so we get divergence of V squared, um, L2 norm squared. That's clearly greater than 0, greater than or equal to 0. But it's not necessarily greater than 0 strictly. And so there's a minor little point which you have to fish around and say, well, we need to show that this whole object here is strictly greater than 0. We almost have it because we have that objects which look like this have at least one component which is greater than 0. We're looking for the supremum. Okay, so if one part of that gives us a number that looks like this, which is greater than or equal to 0, then the supremum, well, what can we say about it? Well, it could be exactly equal to 0, but we're hoping to find that it's strictly greater than 0 once we take the supremum over all possible q. This is just one particular q value for a given v. But we can still show that, I claim. We can still show this, 23.5, which is the same as what I have written here, but I'm going to leave that as an exercise. So we've identified everything except for this one piece, but I'll let that as an exercise, leave that as an exercise to you. 23, Theorem 23.2, there is a unique weak solution to the Stokes problem, and additionally, the pressure solves an equation which looks like this for all V and V perp. Well, the reason the proof is essentially we know that U solution exists in V, and then we can reformulate the pressure equation as done here. And then we can apply the generalized Lax-Milgram lemma to show that this pressure exists. This guy is going to be equal to, or this pressure then is going to be the right pressure for solving the Stokes problem. So we have U that we get first by this argument. Now we can finally get P by this argument using the generalized Lax-Milgram lemma because we've identified everything. And therefore I claim that that allows us to put those two pieces of information together to show that we have a unique solution to Stokes' problem. Additionally, the pressure solves this equation. This one's actually kind of easy because once we know that P solves equation, let's see, I apologize for keep going back. Once we know that P solves this equation, if V is taken to be in V perp, then this term goes away. If V is in V perp, that term goes away by the definition of V perp, and all we're left with is this guy. Okay, so if V is taken in V perp, then the A term dies, and we're only left with the second term. So the solution here follows immediately by the reformulated pressure problem, and using the assumption that V is in V perp. Okay, so that's the proof. We've there's a couple little things to sew up and to tidy up, but that's basically it. All right, so what I want to do then is pause there and take a little break and answer your questions here locally before we get back into the lecture and finish this this result, Theorem 23.3. All right, so now we want to use what we've learned by crafting this Inf-Sup condition, proving that we have unique solutions, and some of the machinery that we've built up along the way to prove a stability result for the Stokes problem. So what does stability mean? Stability means that the solutions to your problem are going to be bounded by the data of your problem. The data of the problem is really just f, the function f. So once we have f, then everything should be determined, and f, the size of f should control the size of u and p. So that if f is equal to 0, this is also kind of a uniqueness result, because if f is equal to 0, then this tells us that u and p both have to actually be equal to 0 as well, right? Because the only way that that could happen if f was equal to 0 is that both of these were simultaneously equal to 0. So basically nothing happening. Otherwise, this gives us what's called a stability result. Notice what appears in this problem. So beta is not really data of the problem. Beta is the structural relationship between the, on one hand, that continuous bilinear form B, and then the spaces of the space of or for our velocity solution and the space for our pressure solution. So this is the beta from the Inf-Sup condition. We want to prove that H1 seminorm of U plus the L2 seminorm, or sorry, the L2 norm of P is less than a constant times the H minus 1 full norm of F. This is the so-called operator norm. How would we define the operator norm? We'll get right to that in a moment. So the first thing is that when we proved that we had when we had a solution to A u v equals f of v, f times v, for all v in v, using the Lax-Milgrom theorem, Lax-Milgrom lemma, then we also, from Lax-Milgrom, you get this result. Okay, you get to, you can show that the H1 seminorm of U is less, or, oh, no, actually this comes from Ries's representation, sorry. There's a weaker result in the Lax-Milgrom lemma, but Ries's representation theorem says that you precisely have that equality. So let's write that there just so we have that. Ries's representation theorem tells us that the H1 seminorm of U is equal to the operator norm of F with respect to V. Okay, so this is the, so if you read the details of the Ries's representation theorem, it has to be the dual space of the Hilbert space that's used in the formulation. Well, that Hilbert space was V, so the dual space has to be V prime. Okay, the dual space, the set of all continuous or bounded linear functionals on V. But I claim that that's less than the operator norm of F. Okay, so what is the operator norm of F? F is, or the operator norm of F is the supremum over all V and H01D of this quotient. F inner product with V over the H1 seminorm of V. Now, the only difference between this object and this object here is that when I did the sup for this object, the sup would be over the space V. But we're doing a sup over a larger space, a larger set. So that means the supremum is going to be bigger. If you take the supremum over a larger possible space, then the supremum is going to be bigger. The supremum here is bigger than the supremum that is used to define this operator norm. So that means that this operator norm has to be bigger than that operator norm. Okay? And let's see. I don't know why I did that, but H minus 1. In fact, why don't we just call it, let's see. It's a little bit, now I know why, now I know what I did that. So, yeah. So I'm going to go back to it. So this is the correct notation. It's just if I wanted to write the dual of this, of the space that I'm interested in, it would be H01D, and then I have to take parentheses and write a dual over that, okay? And that is just what we're defining as H minus 1, okay? That's a pretty standard definition. Okay, but in any case, I defined it with this. This is just the operator norm defined this way. Okay, so this is from Reese representation. This we've replaced with this bigger thing. Using the Inf-Sup condition, remember it's a relationship between the space, the solution space for P and the solution space for the velocity. For any V in H01 D, here's the solution for our pressure equation. Remember, this is just equal to BVP. Okay. Our pressure equation solved this problem here. And now we're going to break this up. Let's use Cauchy-Schwarz. We're going to look at this side here. You can take absolute values of both sides if you want. That would certainly give us something bigger than what we have there. Then, of course, we use triangle inequality with respect to the absolute values, then take, finally, Cauchy-Schwarz. In any case, we'll do a couple of those steps all in one. Taking the Cauchy-Schwarz for this, we get the L2 norm of grad U, L2 norm of grad V, plus, it's not hard to show that relative to your H minus 1 seminorm, we can show that the inner product of F and V is less than the H1 seminorm times this is just going to be the operator norm of F, and this is just going to be the H1 seminorm of V. Okay. If you've never seen that proof before, it follows directly from the definition of the operator norm. I'm going to let you guys recall that or check it out on your own. Now we have a common factor that appears in both terms. I'm going to pull that out. We still haven't applied an Inf-Sup condition yet. We're getting there. We have that, let's see, this object here is equal to, that's just the H1 seminorm of U, that's equal to the operator norm of F with respect to V, but that was less than this operator norm. So we can say that this is less than that, replace it there, and that gives us two operator norms with respect to F. All right, now that gives us an upper bound for objects which look like that. Now divide both sides by this. As long as V is not equal to 0, no problem doing that. We get this quotient on the left-hand side is less than 2 times the operator norm of F. This holds true for any V in H01D. Okay, V was still entirely arbitrary. Now we're going to use the Inf-Sup condition. So this object here is bigger than this object, so it has to be bigger than the supremum of all those objects. Why? Because this is an upper bound. The supremum is the least upper bound, so the least upper bound fits under the upper bound. So there we go. And now our Inf-Sup condition tells us that this is greater than beta times the L2 norm of P. So this, we did all that work, and there's no other easy way to do this, to get a bound of the pressure by some object which looks like this. So now we're going to put the two estimates that we have together. So we already know that this H1 seminorm of U is less than the operator norm of F. Now we just showed that the pressure in the L2 norm is less than something, some constant times the operator norm of F, right? That gives us those two factors, in this sum of two terms, which are exactly the same. So we can use the distributive property to pull that out. And what's left is just a constant, 1 over 2 beta. 1 over 2 beta. And that's precisely what we wanted to show. That's the basic stability of the Stokes problem. All right, so now I'm going to get into this just very briefly. We have the stability we just proved. Now that we have stability and existence and uniqueness, we're ready to talk about a finite element approximation for the Stokes problem. We're not going to get very far in this. That's okay. We can pick up with this topic next time when we come back. So what we want to do for the Stokes problem is what we've done in many other cases. So it's becoming kind of old-fashioned now. We want to come up with finite dimensional subspaces of X and Q. The dimensions of these spaces let's set to be M and N. Okay, we can call them anything we want. Typically, we're going to find, in fact, in this case, we're going to definitely find that M is strictly bigger than N. Okay, the dimension of this space has to be bigger, turns out a lot bigger, or significantly bigger than the dimension of QH. Okay, so those two finite dimensional subspaces are the basis for that process we called the Galerkin approximation process. The next step is, well, if we have finite dimensional subspaces, let's examine bases for both of those. So let B be a basis, B sub X be a basis for XH, and B sub Q be a basis for QH. What is the Galerkin approximation? Well, all we do is we say we're going to make the test function space and the solution space equal to these finite dimensional spaces, XH and QH. We're going to look for a velocity in XH and a pressure in QH that satisfies our weak formulation. So this is just a weak form of the Stokes problem. The only difference is our test functions are going to come from the finite element spaces. In this case, VH from XH and QH from QH. And of course, the definitions of these objects are the same as they were above for the infinite dimensional cases. UV is equal to this object, this bilinear form, and BVQ is equal to this bilinear form. Notice that the interesting thing for A and B is an interesting difference is that the object in the first position and the second position for A comes from the same space. In this case, X or a velocity space. But for B, it's a pairing of a velocity and a pressure. So the velocity comes from the velocity space, the pressure comes from the pressure space Q. Why is it called X and Q? I don't know. It's for historical reasons. All right, now if we can imagine that we have a solution to this problem, all right, of a UH and a pH. So let's do an expansion because they're from the finite dimensional subspaces, XH and QH, we can do an expansion in their various bases, right? So U gets expanded in the BX basis elements, and P gets expanded in the QH basis elements. Now I'm going to define some matrices. Let A be the matrix. This is the so-called stiffness matrix, as usual. Notice that the basis elements for the XH space, because it's a vector space, it's a space of vectors, are each vectors. Okay, so they're vector functions, whereas the basis for the Q space, because it's scalar functions, are all scalars, psi 1 through psi n, phi 1 through phi m. Okay. So now we define a stiffness matrix as before, and we define this weird matrix B, which is not square. The stiffness matrix before was always square. This is the first time you've seen in the context of the Galerkin approximation, a matrix which is not square. And that's because that when we put these various elements into this B inner product, and they're of different sizes, then that makes this B matrix, because we're using the B bilinear form, um, uh, lopsided. Okay. All right. We're a little bit over time, so I'm just going to cut to the chase. We can show that the Galerkin approximation for the Stokes problem has this matrix form. AU minus, we're looking for a vector U and vector P. Now, these vector U and vector P are just the coefficients from our basis expansions above. Okay. Now, remember, coefficient of vectors are always vectors. So we're looking for AU minus, we're looking for V and P that satisfy AU minus BP is equal to F, and minus B transpose U. The second one becomes the transpose. B transpose U equals 0. And so this sets up a non-symmetric or non-square matrix problem that looks like this. And the coefficient matrix can be identified as A minus B transpose and 0. And what you see from this is, in this block form, is that this coefficient matrix is symmetric, but it's not SPD. And so we need some sort of muscle, some sort of theory to tell us that we can invert this thing and get an approximate solution for our problem. And the technology that we're going to use and need is precisely, again, going to be the Inf-Sup condition. That's going to tell us that we can invert this coefficient matrix called C. All right, so that's where we're heading, and you know where we've been. So I'll stop there, and I'll take your questions and end the lecture.